take this average of, say, first n terms of this sequence, okay? Subtract its mean. What would be the mean of this? Can you guess? So it must be mu.
times.
It must be mu. Okay? Think about it. So expectation of x1, x2, x3, so n times mu divided by n, so it's mu basically. Okay? And divided by, you know, what do you call the variance actually, or the standard deviation. And what would be the standard deviation? That would be, can we guess the standard deviation?
Over n, sigma square over n.
So it's going to be sigma square.
Over n.
So sigma over square root of n. Okay? So standard deviation, not the variance. Okay? So standard deviation. Then it says this guy, in other words, take average of the sequence and subtract its mean and divide it by its standard deviation. This is going to converge in distribution to a standard normal random variable. As I'm posting. Okay? In other words, you gather lots and lots and lots of things here. Take their average, and what you are doing, you are standardizing it actually. I mean, if you think. So you are subtracting mean, dividing by standard deviation. So this guy is going to converge, you know, in distribution to standard normal distribution, maybe a normally distributed random variable. Okay. And what is sufficient to show basically? I want to show this. So what should I show? So this theorem is telling you. So what you can show. This will be true. So you have to show that the distribution function of this guy converges to the distribution function of this standard normal random variable. In other words,
Distribution also
okay, that would be will prove this sufficient condition, but this would follow, and if this follows, then you have this convergence in distribution. Okay? Let's prove it. Don't have time. Very easy proof. It's just calculus actually. Okay? Nothing too much interesting. It's a very readable proof. So we're going to prove first for the case when the mu is 0 and sigma square is non-negative. Okay, so assuming that you have a sequence of IIDs for which you have a mean, but let's take that mean 0 and sigma square equal to 1. You will see the other case is just corollary of this idea actually. Okay, so let's prove this basically. In other words, what I want to show, think about it, that the average minus 0 over 1 over the square root of n is converging in distribution to something that is normally distributed. Okay? Since all of these guys are identically distributed, xi's, so these xi's are going to have the same moment generating function. The moment generating function is not going to change because they have the same expectation. So let all xi's have MGF, the characteristic function equal to what is m of t. So let's denote it by m of t. Okay. And now consider the moment generating function of xi over the square root of n. In order to consider the moment generating function of xi of x root of n, I need to compute what? So I need to compute the expectation of the t multiplied by whatever your random variable is. So what is your random variable? Xi by square root of n. And I could be anything. 1, 2, 3, up to n. Is it making sense? But isn't that same as saying that, okay, this is equal to the moment generating function of t over square root of n? In other words, take the moment generating function of xi and evaluate it at t over square root of n. Why this would be the case? Because think about it. What is moment generating function of t? So it's expectation of e to the t xi. Okay? But if you have a t over square root of xi, so there is as evaluate m at t over square root of xi. Is it making sense? Okay. So if you have this, then the next is what would be the moment generating function for this sum now? Okay. In other words, I equal to 1 to n. Okay. So just giving you a sketch, you can read it proof for yourself. So this would be, so what you have to do? So I have to take the expectation of e to the t square root of xi over, okay, square root of n. Okay? But all these guys are independent. So that I can write this as, so the expectation of the product of the random variables, independent random variables, is equal to the product of expectations. So this is same as the product I equal to 1 to n of the expectation of e to the t xi over square root of n. But isn't that like taking this number and multiplying it n times? Because this is fixed actually. It's same for all numbers. All of xi have this moment generating function. So you're going to get this as m over t over square root of n and everything raised to n actually. You got it. Okay? This is very clear. By the way, I'm doing this proof from Ross. I like it from there. So Sheldon and Ross, first course on probability theory. I'll send you this. But you can also read it from the book actually if you wish. Okay, but it's more laborious. I like it. I like it from here. I'm saying, okay, now let's take L of t and define it as log of the moment generating function of t. Okay, take L of t and set it to be the log of m of t. Okay, where we are heading with all this? I want to show the distribution function of this guy, okay, with mu 0 and sigma 1 is equal to what? Is converging, not distribution function, but the moment generating function is converging to the moment generating function of distributed random variable. Okay. So that's what is my task actually. By the way, what would be L of 0?
M of 0 is
So
expectation.
okay, so it will be log m of 0. But m of 0 is what? 1. It's 1, so this guy is 0. Okay? What you can see that if you compute L prime of 0, this would be m prime of 0 over m of 0. So 1 over m of, okay, so it's L prime of t is m prime of t over m of t. So we know all that actually. And therefore this is equal to mu, and which is 0. Okay? Get it? So what is m prime? So if you differentiate moment generating function for the first time, that gives you the expectation, that gives you the first moment. m of 0 is 1. But what is the first movement of the random variable? It's mu actually, but we have assumed mu to be 0. So this guy is 0. Okay? How about L double prime of 0? So this is going to be m of 0, m double prime of 0 minus m prime of 0 square and everything divided by m of 0 square actually. So this is going to get it. So what is it's not. Let's not think too fast. Let's not think too fast. So I can get rid of m of 0, 1 m of 0 from here. Okay. So this is going to be about expectation of x square actually, which is equal to 1. Why this would be the case? Can you see it?
130. अगर m of 0 common लेके divide करेंगे.
Sir, variance is 1, I guess. From variance you have derived.
Yes. So m double prime of 0 is giving you expectation of x square. Okay. If this expression is expectation of x square, then what does this mean? Is that what is?
Sir, so we have taken variance to be 1.
Okay. So xi square actually, not the x square.
We have taken variance to be 1.
1.
And then expectation of x whole
Is
square.
0. So therefore, you're gonna get this equal to 1. Yes. So So you already reached there. Okay. It's not difficult. So this piece of information would be helpful. Okay, so we already did something. So what I want to show now, that m of t over square root of n raised to n converges to, so that's a moment generating function of the sum. It converges toward the moment generating function of standard normal distribution, which is e to the minus t square by 2. Okay. Remember, if x is normally distributed with mu and sigma square, then expectation of e to the tx is equal to e to the mu t plus sigma square t square over 2x. Okay, so that's the general result that you can prove actually. That this would be the moment generating function.
Minus.
I'm sorry?
The minus would come in between.
Where?
E power e.
Here.
Yes.
Yes. So if the and that's it. So just take mu to be 0 and sigma to be 1 and t to be 1 actually. So you get it. Okay? So this is what that I would like to show. But to show this, it is sufficient. So take the log on both sides on this convergence. That's what I would like to show. So if I take log on both sides, it's the same as showing L of t over square root of n converging to minus t square by 2 actually. Okay? As n goes to infinity. So if I can show this, this follows it. And that's it. So what I want to do, take the L of t square root of n, multiply it with n, and try to compute the limit. Okay? So this could come in calculus contest actually.
T is equal to put करने ना पड़े n डाल कर तुम दोनों साइड में चाहिए तो.
So I'm saying that take the log on both sides. That's what I would like to show.
We need to prove the first
one.
Yes, sir. But
I'm saying that if I show this,
yes, sir.
then I can take the exponential and this would be same.
But sir, the problem is how we are going to show this.
Good. This one, how this is the okay. So I mean, if you are not comfortable with this case actually, then we can have an argument actually that why if this follows you can have this actually. Okay, it's not a big deal. So let's compute n goes to infinity. Okay. L of t over square root of n and divided by n power minus 1. Okay, the same quantity I just took this out. And then you have to do what? Use the L'Hopital rule 2 times, because obviously if you're going to put infinity here, things going to explode and things going to sense infinity by indeterminate form. Okay, so you're going to use L'Hopital rule once, okay, and then these facts, you're going to see still you are in trouble, so you're going to use L'Hopital rule again and these facts. So you will see that this is basically minus t square over 2. So I'm not doing it. See it from the top.
Sir,
Ten power minus
we
1.
have to use last period for 2 times.
Yes. At least 2 times.
सर with respect to t करेंगे तो
With respect to n करेंगे.
n लिमिट n
So आप limit n की ले रहे हो, so you have to differentiate with respect to n, not with respect to t actually. Okay? You have to be that much sophisticated at least. Okay? Okay? So just compute it and show that this is true. No. By the way, I wrote this formula correct actually. This must be e to the t square by 2 because I was pretty much sure that this is plus actually. Okay, so this must be plus. So this is what the moment generating function of the standard normal is. So we can show it, you can see the calculation, you can compute this limit, and once you have it, what does this show? This shows this is true, and if this is true, the continuity theorem tells you that the sequence would converge to something standard normal. Okay? Baki rahi baat aakhri. Only 5 minutes. What if the mu is not 0 and sigma square is not 1 actually?
Normalize it.
Just normalize it. That's what we can do. Okay? Let me just quickly give you a hint. You will see that the result will follow from the same theorem. How about if mu is not 0 and sigma is not 1? In other words, you have this generic case. Then what should be? Then consider this guy. x1 plus x2 plus x3 over n minus mu over sigma over square root of n. Okay? See? You have an ideal thing in front of you. So see, try to make some changes in such a way. Okay, try to choose these xi star in such a way. Okay, so that if you evaluate them, you get this. Okay, but these xi star should be that expectation of xi star is equal to 0, and variance of xi star must be 0. So we tried many. Who knows what would be that? But, that's what you have to figure it out. And what you can do then is that if you are breaking down to something that you have already done, and the result is true for this, and this is converging to, for example, normally distributed in, what do you call, in distribution. So this would also. Okay? So the question is, what should be this? And who knows that? See the book for yourself.